Okay, I'm going to record lecture 4 on transformation of a continuous random variable. So let's recall a continuous random variable x that are sampled from a probability density function f for x. So here, this f denote a probability density function, and we attach this capital X to denote that this is a density function of the random variable x. Recall that we use capital letter to represent the random variable, and we use lowercase letter to represent the random variable. And so this is a function of x. And here f of x is like a name. F is a last name, and x is a first name. So this is a whole notation, inseparable single notation, meaning that this is a density function of random variable x. And this function is a function of small x. So we sample the random variable from this density function, and we can draw a density function as a function of this small x. But what's the intuitive meaning of that? So you can consider a density as describing a very big population of n points. For example, n is almost infinite. And these n points can be described by a density function. That is, if you look at the scatter plot of these n points, say n may be 300 million for the US population, and the x is a height for a random person. And then if you plot the heights of all the 300 million people, you have a cloud of points, right? And it's denser here, less dense here. That's why you have such a density function. And then random sampling, so sample x from this density, just means that you randomly sample a person from this population, or randomly sample a point from this cloud of points. And then you get a point, and you look at where the point is. So that will be your capital X. So this is a more intuitive way to think about sampling the variable x from a density function. And you can treat this as sampling from a population of points whose density is described by f of x. So that's the basic idea. And so you see this is denser, right? This is less dense. So and then you have this curve. In particular, so if you look at the number of points in a very small bin, so delta x is effectively infinitesimal. So eventually we let delta x go to 0. And we let n of x to denote the number of points in this small bin. So this n of x, so that's the number of points. And then we divide this by the total number, capital N. So this gave us the population proportion for the points in this small bin, okay? And now let's think about, we randomly sample a point from this population of points. And then we have the probability, right? So before random sampling, we just have a population, deterministic population described by a density. So there's nothing probabilistic. However, if you randomly sample a point from this population of points and let x be the point that you get, then the probability that the point belong to this small bin, that will be the population proportion of this small bin, okay? So we are just talking about, again, axiom 0 in probability theory. So that is, if you randomly sample a person from the population, then the probability is the population proportion. So that's the basic idea. So under random sampling, the probability that x belong to this small bin will be the population proportion of this small bin. So this gives us this probability, and this probability equal to f of x, delta x, according to how we define this density. So that is even before sampling, this population proportion is fx delta x. Or in other words, before the sampling, when we try to describe the population density, then f of x, the density is actually n of x divided by delta x, say the number of people in Los Angeles divided by the area of Los Angeles, then we get the density of Los Angeles. But usually we also normalize this number by this n. We divide this nx by n so that this gives us a proportion. So the proportion divided by delta x, we get the density. Or in other words, proportion is the density times delta x. So at this point, as I said, there's nothing probabilistic, everything is deterministic. But if you randomly sample a person or sample a point, then this population proportion becomes the probability that the point, the random point, fall into this small bin. And since this population proportion equal to fx delta x, therefore this probability also equal to fx delta x. So therefore, this f of x, even though it describes the population, there's nothing probabilistic, but under this random sampling, then f of x also describe the probability that the random point fall into this small bin divided by delta x. So that's why it is called a probability density function. So before sampling, it is density function of the population. You can call this as a population density function. But after you do this sampling, then you can also have a probabilistic interpretation, because under random sampling, probability is simply just a population proportion according to axiom 0 about the probability under equal likely setting. Okay, so therefore you see f of x then equal to this probability that x belong to this small bin divided by delta x. So this is a probability, and if you divide this by delta x, you get f of x, which is a probability density. Or in other words, this probability is simply the density times delta x. And if this is f of x and we have delta x, we actually get the area of this small bin, small rectangle. Okay, so that's how we understand this notation. We sample x from this density function. I just want to make things as intuitive and as tangible as possible. And then now let's think about the transformation. So suppose that we transform this x to y by this transformation, this function h. So let's assume that this transformation is monotone increasing so that it preserves order. It can also be monotone decreasing. Later on, we will see such an example. But now, for simplicity, let's assume that this transformation is a monotone increasing, and it is invertible so that we can have x equal to g of y. So g is the inverse of h. Okay, and then we can also, if we randomly sample x from these population points, we can also transform x to a y. So y is the transformed value of randomly sampled x. Okay, but if you look at the population, so the same population of endpoints will be transformed to another population endpoints. So originally we have the population endpoints on the x-axis. After transformation, we have population endpoints on the y-axis. And then you can see that the density may change under such a transformation. And you see that it is denser here, right? But if the slope is very big, then it is less dense here. So that is the transformation, continuous differentiable transformation actually can change the density. And maybe we can also take a look at another situation. So another illustration of this basic idea. So this time, instead of plotting x on the horizontal axis and y on the vertical axis, so we can plot both x and y on the horizontal axis. So we have x, we have endpoints, right? And let's assume that we have monotone transformation that preserves order. Then it is possible that you transform one density to another density, and even to a density of totally different shape. For example, this density has one mode, but then this density, we may have two modes. That is, we have a lot of values here, a lot of points here, and a lot of points here, but in the middle, there's not many points. So therefore, the density is high in this place and high around this place. So it's a bimodal, you have two modes, right? So that's a very different density, but it is possible that under this monotone order preserving transformation, you can actually transform these endpoints, this population of endpoints, to this population of endpoints whose distribution can be completely different. Okay, so this is another illustration. And also, as I mentioned, in this transformation, the slope of this transformation play an important role in changing the density. So you can see that here, if the slope is along this y equal to x, right, you don't change the density very much. But if the slope is very small, you actually change the density, it becomes denser. The reason is that this delta x is being mapped to a smaller delta y. But if the slope is extremely high, then a small delta x will be mapped to a much bigger delta y. So this type of stretching or squeezing of the size, or we may call this as space warping, actually determine how we change the density. And specifically, suppose we have population, so we have a lot of points. Now let's focus on this small region. So we have some points here. All the points, suppose we have nx points in this small bin, and they are all mapped to the nx points, the same number of points in this the corresponding bin, where x is mapped to y and x plus delta x is mapped to y plus delta y. So suppose the number of points in this bin is n of y, then we know that because this is a monotone transformation, so all the points here is mapped to the point mapped to the points here. So nx equals ny. Okay, so that's a key observation under the mapping, so that we map one population points to another population points, so that all the points in this small slice is mapped to the points in this small slice. So therefore, nx equals ny under this mapping. And if we divide this by total number n, we have nx divided by n equals ny divided by n. And this under, now let's think about the sampling, random sampling. If we randomly sample a point, let x be this random point, then x is mapped to y. And the point is that if x fall into this small bin, then the corresponding y will also fall this small bin. And recall that this ratio, this population proportion under random sampling becomes the probability that x belong to this small bin. And this probability ratio, this population ratio, population proportion become the probability of y in this small bin. So that is because of this, this population proportion is the same as this population proportion. Then under random sampling and the transformation, then this probability equal to this probability. Or in other words, the event that x fall into this small bin and the event that y fall into this small bin, they are equivalent event. Okay, so therefore the two probabilities are the same. They're equal to each other because the two events are equivalent to each other, meaning that if one is true, then the other must be true, and vice versa. And remember that this population proportion of this probability is nothing but f of x at x times delta x, right? And this one similarly is f sub y of at y times delta y. So they are equal to each other. And now you can see that you can then relate the density for fx and fy based on how delta y is changed to, how delta x is changed to delta y. So this equation, or this equation, this is a key equation for the change of the density under this continuous and differentiable transformation. Okay, so I want you just to memorize or memorize this equation or this equation, because the rest, I don't need you to memorize the rest, because the rest can be derived very easily as long as you start from here. Okay, so there's no need to memorize the result that follows. You only need to memorize this identity, and the rest just follow very easily. I think it is here. So now let's look at, let me see if it is here or, yeah, I think it is here. Okay, so now let's think about one example. So suppose that we want to generate this random variable t now we use capital T to denote this random variable because it is waiting time. So T follow exponential 1. Usually it is exponential lambda, but let's look at the special case, exponential 1, so that the density for x, the density for t, f of t is the e of negative t for t to be greater than or equal to 0. Okay, so that's the density of t. And our claim is that if we generate U from uniform distribution, so U is from uniform 0, 1, and if you take negative log U and you let this be T, then T follow this density. Why is that? We want to prove that. Actually, we derive this, this transformation, this method of generating exponential random variable based on inversion method. But the inversion method is actually a special case for the transformation method. So inversion is but a special case for a transformation. So it can, now let's just treat this as a certain transformation. And we know that ft t delta t equal to fu u delta u according to the identity that we just established. We just changed the notation a little bit, right? And then from here, we can then derive the density of T. So Fu of U, this equal to 1 because it is a uniform density. Actually, I think there's some line here. I don't know why it come to here. So the reason it is 1 is because if you look at the probability that a uniform random variable belong to this small interval, then this probability is simply the length of this interval. So this U plus delta U, and then this probability is delta U. So therefore, the density is 1 because it's 1 times delta U. Or here, this probability, the probability here is just a delta U. Again, this should be delta U. Okay, so now we have this identity, and from here we can get FTT. The density of T is a delta U divided by delta T. So that is a ratio between the change of the neighborhood. And here, this is actually a monotone decreasing function, the transformation between T and U. So therefore, we should take the absolute value because this derivative, so here we have T equal to negative log U, right? So that's a transformation. And the inverse is U equal to E of negative T. And here we want to compute delta U divided by delta T, which is the derivative of this transformation, which is a negative E negative T. And because it's this monotone decreasing, right? So the slope is negative. However, here, when we calculate the density, we actually only care about the size of the neighborhood. So the sign doesn't matter. So that's why we take absolute value in this case for more general. And then it is E of negative T. So now you see we derive the density of T is an E of negative T. Okay, so that's the basic idea. So that is this actually proved that indeed this transformation gave us the desired random variable that follows the desired target density function. Okay, so now let's continue with another example, and based on what we already have. Suppose we already know how to generate the T from exponential 1, so that the density of T is like this. Okay, so we just make this more concrete. I give you 2 concrete examples. And now let's assume that we have another transformation like R equal to square root of 2T. So T is always non-negative. So square root 2T is always defined, and we let R to be negative to be square root of 2T. Remember that the T is generated from U by negative log U, right? So, and then R equal to square root of 2T. So this is actually square root of negative 2 log of capital U. Okay, so this gives us a transformation. So here I use a lowercase letter just to denote this transformation. So R is negative square root of negative 2 log U, because the T is negative log U. We just plug in negative log U here. We get this transformation. So under this transformation, we want to know what's the density of R. Suppose we know the density of T, which is here. This is the density of T, and we want to know what's the density of R. So, and then based on this identity. So now we come to this identity. Again, the same as the identity here, except that we change the notation, right? So we still have ft delta t equal to fr small r times delta r. So we always start from this identity. And this transformation is that r equal to square root 2t, and the inverse transformation is t equal to r squared over 2. Okay, so we have this transformation. And from here, then we know the density for t, right? So which is e of negative t. Okay, so therefore you see from this identity, we know that fr of r. So fr, so this is not one, this fr of r equal to what? Equal to ft and then times delta t divided by delta r. We just move delta r to this side. So that fr small r equal to f capital T small t times delta t divided by delta r. And we know that t equal to r squared over 2. Okay, so then therefore delta t over delta r is r. The derivative of this function, the derivative of this function is r. So therefore, the density of r, again, this is r, f capital R of at this small r equal to e of negative, because t equal to r squared over t, we just plug in r squared over t over 2, sorry. Then we have e of negative r squared over 2 times r. So this is the density for this random variable r after this transformation. Okay, so I think in this lecture, I first gave you the intuition of the transformation, the change of the density under the transformation. And then I gave you this formal way of calculating the change of the density under the transformation. Okay, so you always start from the equation like this, and then the rest can be based on taking derivative for the underlying transformation. Okay. So this is a preparation. So I hope that from here you can understand that the density may change under the transformation, and also you learn the technique to calculate the density and of the new random variable if it is a transformation for a known random variable with a known density function. And also remember that in homework 1, we studied one method for generating a normal random variable, in particular, the standard normal random variable with mean 0 and variance 1. So the density of a standard normal random variable is 1 over square root 2 pi e of negative x squared over 2. Okay, and we use the inversion method to generate it. However, we have to use a rather tedious function, right, formula to approximate the inverse of the CDF, cumulative density function, using the inversion method. And that approximation is only approximate, so therefore it is not really extremely accurate. So in today's lecture, after the preparation on transformation of the random variables, we want to develop a method based on a different transformation to generate normal random variables. And in order to make things simpler, actually, we want to generate two independent normal random variables simultaneously instead of generating a single one. So the strange thing here is that when we look at the two random variables together, life is actually easier than looking at a single random variable. More specifically, let's think about, we also generate another random variable y, follow normal 0, 1, and x and y are independent. So the density of y is 1 over square root 2 pi e of negative y squared over 2. And again, we assume x and y are independent. So what's the meaning of that? Remember that when we say we generate x from this density, so we have a density, we have a population of endpoints and distributed on this x-axis, and they have this such a density, so that 95% of the points in this population of endpoints is between -2 and 2, and the density follow this so-called bell shape. And the point for generating two random variables x, y independently from the same density means that you draw you sample one point from this population, and this is your x. And then you put this point back, and then you sample another point from this population, this is your y. Okay, so that's the idea for generating two random variables. It's like you just randomly sample two people from the big population of 300 million people. Okay, but what do we mean by independence? So here, let's think about a simple example of rolling a die. So suppose we roll a die, then we get a number, right, from 1 to 6. And suppose we then roll the die again independently, we get another number y, which is also from 1 to 6. What do we mean by x and y are independent? So that actually means that if we look at the x and y, so x can be from 1 to 6, y can be from 1 to 6. So we have how many pairs? We have 36 pairs. So independence here means that all the 36 pairs are equally likely. Okay, so if you just sample, suppose you roll a die once, a fire die once, then all the 6 numbers equally likely. But if you roll the die twice independently, and then you got 2 numbers, so they are independent, means that all the 36 pairs are equally likely. So this is a notion of independence under this equal likely sampling. And we can generalize this notion to this more general sampling. Suppose we sample xy from f of x or f of y, so from the same density. And then here, if you look at x and y, so here you have 36 pairs, right? But here you actually have n squared pairs, not the points, n squared pairs for xi, yj. So suppose we label those points as x1, x2 to x capital N, right? And we can also use y1, y2 to capital Yn to label the same points. And then we have n squared pairs of xi, yj. And all these n squared pairs are equally likely if x and y are independent. Okay, so that's the intuitive, hopefully tangible notion of independence. Okay, and then if they are independent, as I mentioned, if they are independent, then all the n squared pairs are equally likely. So as a result, if you look at the first number, the probability that the first number in this small range and the probability the second number in this small range. Okay, so x in x plus delta x and y in y plus delta y. This actually equal to f of xy delta x delta y. So this is a generic definition of a two-dimensional density. So we just generalize the definition of the density from one-dimensional to two-dimensional. So it's like if you look at the small, say small range, right? Small range. So what's the probability that, or what's the population proportion for the points in this small range? So this population proportion among these n squared pairs, this time the population become n squared pairs. So this proportion in general, so if we have x and y as random variable, in general, this is defined as a density times the error because it's a 2D, right? In 2D, the size becomes the error, delta x times delta y. So this probability, joint probability, is a density times delta x delta y. So this is the general definition. No matter whether x and y are independent or not, where this probability again can be interpreted as a population proportion if we randomly sample a point from this big population point, if each point is a 2D point with 2 coordinates, x and y. But if they are independent, then this joint probability equal to the product of each individual probabilities. Okay, and as a result, then the joint density is actually the product of the marginal density, so that you only need to multiply the two densities. Remember that f of x is 1 over fx is here, okay, and f of y is here. So if you multiply them together, you have 1 over 2 pi instead of square root, right? And also you have e of negative x squared plus y squared over 2, okay? So, and then here you have this this one. So it's 1 over 2 pi e of negative I squared plus y squared over 2. So this is the joint density. This joint density is actually simpler than each marginal density because you don't have square root anymore. And moreover here in this two-dimensional domain, so you see this density only depends on x squared plus y squared, which is the distance from this point for each xy, okay? So suppose xy is here, the x squared plus y squared is r squared, where r is the radius or the distance between this xy to the origin, okay? So therefore, if we use the polar system, so the density become 1 over 2 pi and e of negative r squared over 2, where r is the distance from xy to the origin. And now you see it is simpler because the density only depends on r. It has nothing to do with the direction. Let's call this direction as a theta. So it has nothing to do with theta. The density only depends on r. So no matter what the theta is, the density is always the same. So this is isotropic. That is, you see the same thing at any direction. So therefore, if you look at the distribution of theta for a random point of this isotropic cloud of points, which means all the directions, they look the same, then the angle, the theta, is actually uniform. It can be any direction with the same probability. So therefore, under the polar system, so suppose we have xy follow normal, not 1, 0, but 0, 1, normal 0, 1 independently. And then under the polar transformation, we represent x to be r cosine theta, y to be r sine theta. Then this theta actually follow a uniform distribution. Okay, so theta follow a uniform distribution. And what's the distribution of r? So let's assume that the distribution of r is f of r. So that's the density. Okay, the density of the radius of the point, where r is the square root of x squared plus y squared, and the theta is arctangent y over x, which is the inverse of this polar transformation in the previous page. Then we want to know the density of f of r. And the density of f of r is a probability that this r in this small range divided by delta r, right? And what's the density? So we want to calculate this probability. What's the probability that r is in this small range? So what's the meaning that r is in this small range? The meaning is here. So if r is from this r to r plus delta r, so that means the points lie on this ring. So this ring from r, where the any point in this ring has this r, where it's bigger than this small r and smaller than r plus delta r. Okay, so this defines this a small ring. And the probability that r is in this r to r plus delta r means that we want to know what's the population proportion or the probability of random point belong to this ring. Okay, and we know that the density on this ring, if delta r is infinitesimally small, then the density is here, 1 over 2 pi e of negative r squared over 2. So this is density, right? And we want to calculate the probability on this ring. So we already know the density, and the density on this ring is the same, no matter what theta is. And then the probability of this ring would be the density of this ring times the area of this ring. So the area of this ring is the length of this circle, which is 2 pi times r, and times the height, which is delta r. Okay, so therefore, we can calculate this probability that r, the probability that r is in this small range, which means xy, the point, fall into this this ring, is this density. We have this density f of xy, this density times the size of this ring, which is 2 pi r. This 2 pi r is the length of the circle, and times delta r, which is the height. Okay, so that's the basic idea. And then you see that this density is here. And here we have 2 pi r times delta r, and 2 pi get canceled. So we have this probability that r, the radius, is in this small range. equal to E of negative R squared over 2 times R, delta R. And if you divide this by delta R, so that the density will be E of negative R squared over 2 times R. So that's the density, probability density for this R. Okay, and this is exactly the density that we have studied in our preparation. So that is this R, this random variable, which is square root 2 times the exponential waiting time, which itself can be calculated as negative log U, where U is uniform. So this R follow exactly this density. Okay. So therefore, we can actually generate this R very easily as a negative 2 log of U. Okay, so we can generate R as a negative 2 log U, which is here. So this R is a negative, so, sorry, this negative should be inside. R is negative log U. Okay, so this is how we generate R. And theta is uniform from 0 to 2 pi, right? So theta is uniform from 0 to 2 pi. So this is 2 pi U. And the theta and R are independent. No matter what theta is, R always follow the same distribution. So therefore, we use U1 here to generate theta. We use U2 here to generate R. And we let U1 and U2 to be independent of each other. Remember, this negative should be inside of square root. Okay, sorry for the typo. And then we let U1 to be U2, U1, U2 to be independent of each other. So that theta and R also, they have nothing to do with each other. So therefore, we can generate theta and R using this very simple method by first generating U1 and U2 independently and perform the transformation with this negative sign inside. After we get theta and R, we can then let X to be R cosine theta, Y to be R sine theta. This way, we actually generate two random variables that follow normal 0, 1 independently. Okay. So this method, everything is exact. So unlike the inversion method, where we need a very complex formula to approximate the inversion of CDF, capital F, or calculate F inverse. We don't need approximation here. Everything is exact. And also the calculation is much simpler, right? This formula with this negative sign inside. This is a much simpler formula. And then we can also generate two copies of independent normal random variables at the same time. So therefore, this is a go-to method, a preferred method. Okay, but in the previous homework, I asked you to use the inversion method to generate this normal random variable. So it is just for you to gain some understanding of the inversion method. But this method is a go-to method. Okay, so now let me briefly mention this notion of independence. So back to independence. So we want to know what's the probability that if we generate X and Y, right, we draw X, Y from the same population of endpoints, capital N points independently. And then I claim that then we have N square pairs, right? Then all these N square pairs are equally likely. So therefore, if you calculate this probability, you just count the number of 2D points or the number of pairs that are in this this range. Okay, this small cell. Okay, and because you just all those N square pairs are equal likely, right? You just count how many X in this bin and how many Y in this bin, and then the number of pairs will be the number of Xi in this bin times the number of Yi in this bin. Okay, you just you count the number of pairs by the multiplication rule, and you divide this by the total number of pairs, which is N squared. So this N squared. So the point is that you can factorize the probability, joint probability into the product of marginal probability comes from the fact that the number of pairs in this small range is actually the number of Xi in this small bin multiplied by the number of Yj in this small bin, because you pair them, you cross them, you pair them. So the number of pairs is the number of the points in this small bin, the number of X in this small bin, and the number of Y in this small bin. You multiply these two numbers, you get the number of pairs. So this underlies the reason we can multiply the density we can factorize the joint density to the marginal density, because then you divide each number by n, so you get this probability, right? This population proportion. Under random sampling, it becomes the probability. And then this joint probability can be written as a product of the marginal probability. The reason we can write this factorized form is because of this result. Okay, so that is the number of pairs is simply just a number of xi times the number of yj. Okay, so that's the reason. Another illustration, let me go slightly further. Another illustration for the independence. You can think of y1, u1 and u2 follow uniform 0, 1, and they are independent, just like what we have here, right? We assume u1 and u2 to be independent, which means, again, in the equal likely setting, that all the pairs of u1, u2, each pair of u1, u2 become a point in this unit square. So all the points in this unit square are equally likely. So that's the independence. And under this situation, let's think about the probability that u1 belong to A and u2 belong to B. Okay, and then the probability of A and B is that u1, u2 as a coordinate point, the point belong to this small rectangle. Okay, which is area of this rectangle. What's the probability that the point belong to this small rectangle? It is the area of this rectangle divided by the total area, which is 1. So this is just area of this rectangle, which is the length of A times the length of B. So that's area. Okay. So here you actually also get the notion of factorization based on the mathematical fact that the area of this rectangle equal to the length of A times the length of B. So that's why you have P probability A and B equal to probability A times probability B. So in other words, if A and B are independent, then probability A and B equal to probability A times probability B. Okay, and similarly as what we have here, so if X and Y are independent, then the probability of the joint density of XY, which is this probability, right? This probability divided by delta X, delta Y. So this equal to the density of X, which is this probability divided by delta X, times the density of Y, which is this probability divided by delta Y. So that is in this equation, if you divide both sides by delta X, delta Y, then you get this result. That is, the joint density can be factorized into the product of the marginal densities. And this factorization is based on this orthogonal notion, right? This notion, they are orthogonal. Similarly here, so these two directions, they are orthogonal. And then we use this orthogonal notation to denote independence. So here we talk about the independence of the event, and this is the independent of the random variables. Both actually admit this factorization form. So the joint probability can be factorized as a product of the marginal probabilities, or the joint density can be factorized as a product of the marginal densities. I also want to just mention a little bit about this A and B. So if you treat this interval, unit interval, as your sample space, then this A is a subinterval, and then the probability of A is the length of A. But if you treat your whole unit square as your sample space, then your A become this vertical stripe, okay, vertical zone. And then the probability of A is still the length of A because the height is 1, right? So the area of this vertical zone is length of A times 1, which is also the length of A. So that is, you can think of A, or the probability of A, within two different samples spaces. One is this unit interval, the other is unit square. But in both situations, the probability of A is the length of this interval A, okay? So we have studied this another method for generating normal random variables based on the transformation. And now with equipped with that, we can do Monte Carlo simulation and also later Monte Carlo integration. And I think here I want to just go back to the very basic notion. And again, I want to remind you the intuition. of generating X from a density. So here, a density, as I mentioned before, can be think about a population density for a deterministic fixed population. Only when you randomly sample a point, and then you get the randomness, you get the probability, and this random point is said to follow f of x. Okay, so here everything is fixed. We have population of n, where n is almost infinite points, for example, 300 million. So this is deterministic. But if you perform a random sample repeatedly, you sample, say, n points. So each point follow f of x. Okay, so each point is a random sample from this capital N points. If you do this small n times, so this small n may be 10,000, which is much smaller than the size for the population, which is effectively infinite. Okay, and then if you plot a histogram, okay, then this histogram is actually an approximation of the density. However, because these endpoints are random samples, so if each of you in this class generate 10,000 points, sample 10,000 points from the same population, then each of you will have your own 10,000 points, and they are different, right? If each of you will hold a different set of points, okay? So that's why this is random. So each point is random, and the sample of n points is also random. And if you plot the histogram, you're going to get something random. It can fluctuate. Okay, so that's the notion. So the population is fixed, and under random sampling, then the probability become population proportion. For example, what's the probability you get a point below X? That will be the population proportion of the points below X, which is capital F of X, right? And but if you do the random sample, then the probability reflect itself as a frequency, right? How often you get a point, say, below X, or how often you get points within this one. So this frequency can be random if this n is finite, unless this n also goes to infinite, become infinitely large, then this long run frequency will converge to probability. But for finite n, certainly there will be randomness, statistical fluctuation. But nonetheless, we can think of probability as a long run frequency. And similarly, if you look at this example, similarly for the canonic example 2, okay, so which we also use the geometric situation. So we have this region, suppose this is a unit square, and then we have this A, which is a sub-region within this unit square. So again, we can think of the population consists of all the points in omega. And if you randomly sample n points, it is like you just throw n points randomly into this region omega, right? And then what's the frequency, how often the points fall into A? So let NA be the number of points in A. Then even if you fix this n to be 10,000, then this NA can be random. So that is, suppose each one of you in this class do the same experiments, that is throw 10,000 points randomly into this omega. Then if you count your NA, so each of you may have your own NA, and NA is not fixed, it can be random. So that is, if we look at the frequency, NA divided by N, so this is how often A happens. And this frequency actually also fluctuate because it can be random, but it will fluctuate around this probability of A, which is the area of A divided by the area of omega. So here I want to use this example again to illustrate the idea that this frequency actually can fluctuate, and it fluctuates around the probability. But if n is very big, then this frequency, the long run frequency, will converge to probability. So therefore, when you think about the probability, you can think about you randomly sample from a population, so that probability is simply the population proportion. But you can also think about probability of A in general as how often A happens if we repeatedly doing the same experiment. That is, you can also think about probability as a long run frequency. Okay, so either population proportion, which is fixed, all long run frequency. And if n is fixed, this frequency may have statistical fluctuation. But if n goes infinity, then the statistical fluctuation will diminish. So you can think of probability not only as a population proportion, but you can also think about probability as a long run frequency when you repeat the experiment again and again. So those are the intuitions to think about probability density and the probability in general. Okay, so I think I can stop here.